Howdy. Welcome. So, here we go with Unit 5. It's called Other Functions. That's the generic name that I've come up with for this. It's the best I could come up with on such short notice. But as we move through, so the basic thing is how can our knowledge of differentiation and integration be extended to other elementary functions? So all the things that we've been doing with derivatives and integrals, we've been doing with the trig functions, we've been doing with our basic polynomials, and now we're going to branch out to other types of functions. And so there's a list of things that we want to know and understand and be able to do. I'll give you that handout so you'll have it, but talking about the natural log function, talking about e, and talking about inverse trig functions, and still clinging to the fact that differentiation and integration are interdependent, and that patterns are the big helper. And we want to be able to find derivatives, find inverses, find derivatives and antiderivatives. I'm with me now. Find derivatives with natural logs, with e, with trig functions, and solve problems with inverses and exponential functions and inverses as well. Okay, so that's the big picture. Basically, what happens is we learn about something new, then we learn how to take its derivative, then we learn how to do the integral, and they're all interdependent as we move forward. So let's get on with it, shall we? So, properties of logarithms. That's what the title of the video is. That's what we're talking about. And the question is, what is a logarithm? Okay? Hold on for a sec. All right, I decided the calculator would be helpful. And so, it's here and it takes a few seconds to get it up. So the question is, what's a logarithm? And so let's just play around with what's a logarithm. So if I was looking for the log of 100, and I'm not closing the parentheses. Oops, that's the log of 1,000. So the log of 1,000 is 3. What's the log of 100? Darn it. Hold on now. I can do this. The log of 100 is 2. And so you might be going, hey, look, might have something to do with the number of zeros. So what's the log of 10? Log of 10 is 1. Okay, so that's great. So it seemed like it would have something to do with the number of zeros. It's got 3 zeros, logs 3. This is 2 zeros, logs 2, 1 0. But what if a number doesn't have any zeros? So what if it's like 57? It's a funny number. Log of 57, 1.75. Okay, so 1.75. Notice that the number 57 is between 10 and 100, and notice that its logarithms between 1 and 2. Okay, if we just a back way ahead of here, I don't know what I'm saying, but to get to the big picture, if I take 10 and raise it to the second power, I get 100. If I take 10 and raise it to the first power, I get 10. If I take 10 and raise it to the 1.7558748556 power, I get 57. Okay, so question answered. What's a logarithm? A logarithm is just a fancy exponent. Okay, that's all it is. It's an exponent. Don't get scared by the name. If you just remember it's an exponent, it's a fancy exponent, it's a highfalutin exponent. That's what it is. Okay. What's a natural logarithm? A natural logarithm is an exponent with a base e. Okay, and e is that 2.71. It's another one of those constants that like pi. 2.71828, and then it keeps going forever and ever without doing repeating things. It's an irrational number. So a natural logarithm is just a exponent base e. Logarithm that we push when you push the log button on your calculator, you get base 10. All right. So what's a logarithm? It's a fancy exponent. I'll just keep saying that over and over and over again. So when we say something like the log base b of a is equal to x, it means this number raised to this power. This number raised to this power equals this. It's kind of a weird sentence. So it's kind of like saying b, the base, to the x power, x is my logarithm, is equal to a, my number. So let's play a little bit. Okay, the log base 5 of 25 is, so the question is 5 raised to what power equals 25? I know you're thinking it. 2. 5 squared is 25. Okay, this one's asking what number raised to the third power equals 27. Okay, b to the third power equals 27. That's what it's asking us. And so the answer is b equals 3. And finally, 4 raised to the third power equals what number? 4 to the third power equals 64. So x is 64. Okay, logarithm's an exponent. Just remember that. Logarithm's an exponent. What's a natural logarithm? Same sort of thing. Okay, but we don't write the base down here. Typically, we don't write, if it's just a regular log, base 10, we don't write the number. If it's some other base, we write what number it is. But natural log, okay, log natural, which is French, I think. I'm just going to pretend that. Okay, natural log is base e, so there's no base there. It's this number, e to the a power equals x. Okay, and we tend to use natural logs in here as we move forward. So, a logarithm, it's a fancy exponent. It behaves like an exponent. Okay, so I will tell you that the natural log of 1 is 0. Okay, and in terms of exponents, that's like saying a to the 0 power equals 1. Anything to the 0 power equals 1. The natural log of 1 is 0. So e raised to the 0 is 1. It's an exponent. The natural log of a times b is equal to the natural log of a plus the natural log of b. So if I have a to the m times a to the n, what do I do with the exponents? That's right, I add them. Okay, so it behaves like an exponent because it is an exponent. So we can break multiplication down into addition. Just like when we're multiplying exponents, we add them together. Same story. Okay, if I have the natural log of a number raised to a power, what I can do is I can bring that power out into the front, and I can multiply it. Okay, situation there from logarithms, a to the m raised to the nth power, what would we do? We would multiply those two exponents together. Okay, the log of a is an exponent. Raise that exponent to an exponent, we're just multiplying them together. So we multiply the exponents so we can bring that down in front. It's a very helpful little process. And finally, the natural log, I don't know if it's finally, maybe there's more. No, it's finally. The natural log of a divided by b is equal to the natural log of a minus the natural log of b. And similarly, if I have a to the m, it's an m, divided by a to the n. That looks more like an m. Okay, sort of. I subtract the exponents. So with division with exponents, we subtract. Division with logarithms, because they are exponents, we subtract. Okay? Same sort of thing. Fancy exponents. Highfalutin. All right. So we're going to use those properties to expand and do some things. So the natural log of x times y is just the natural log of x plus the natural log of y. The natural log of x squared, using that second property, is going to be 2 times the natural log of x. And this one's going to take a couple steps. We've got division going on. So this is going to turn into be the natural log of x squared minus the natural log of y cubed, which we would further adjust by bringing the exponents down in front. And so we're going to have twice the natural log of x minus thrice the natural log of y. So thrice. Okay? So that's how those work, expand. We can also, well, do something with something a little more complicated. We've got, some addition and subtraction and that sort of thing going on. So what I would do is to expand this out. I would write this as the natural log of x plus 1 cubed plus, because we're multiplying, the natural log of x minus 1 squared, minus, because we're dividing, the natural log of 2x minus 5 to the 1/2 power. Okay, remember, we don't worry about the square rooty thing. And then we would just use that last property and rewrite this as 3 natural log x plus 1 plus 2 natural log x minus 1 minus 1/2 natural log 2x minus 5. Okay? And believe me, this turns out to be a really helpful thing when we start taking derivatives of these. Right now it's just fun practice, right? Right. So the other way is we can tract these things. We can turn it back into one single logarithm. And so, where it used to be addition, it's now comes multiplication. Where it used to be division, it now becomes, it used to be subtraction, it's now division. I don't know what I'm saying. So typically when we end up with these, we have one natural logarithm, one time. Okay? And so I'm going to bring the exponents back into the picture. Okay, this becomes an exponent again. And so this becomes the natural log of x cubed times x minus 5 squared over 3x squared plus 4 to the 1/3 power. Okay? And these are come back up as exponents. And then what used to be addition is multiplication. What used to be subtraction is division. Because they're just exponents, they behave like exponents, so we can rewrite it as one solid expression. Okay, we'll kind of walk our way through this one as well. Notice the squared's outside this whole thing, so we're going to worry about that a little later on. Okay, right now we're just going to condense what's inside the major parentheses. So I'm going to have the natural log of 3x. And the other two things are subtracted, so they're both going to turn out to be division. X minus 1 cubed, as this goes back up as an exponent, times x plus 5 squared, as this goes back up as an exponent. Okay, and then what do we do with this exponent right here, this 2 that's multiplying the whole thing? Well, it's squaring the entire process, so it goes out like that. Okay? Contracting. Super duper. So we can use these to figure out some things, if we know a couple of pieces, and this is just a sort of an exercise in working things out. So natural log of 0.25, that's like the natural log, of course, of 1/4, which we know to be the natural log of 1 minus the natural log of 4, which we know to be the natural log of 1 minus the natural log of 2 squared, which we know to be natural log of 1 minus 2 times the natural log of 2. Are you with me? That's where it came up there. All right, and you may or may not remember, but the natural log of 1 is 0 minus 2 times 0.6931, which is some number that we would use our calculator probably to figure out. Well, we could do the math on it really quickly. 1.2, 1.3861 or something like 862, something like that. You can do that negative. So the idea is we can manipulate these. Use if we know a couple of things, we can work our way through. But of course, your calculator's got a natural log button on it, so you probably would just do that. But natural log of 24 in terms of 2's and 3's, I think is the natural log of 8 times 3, right? Which is the natural log of 8 plus the natural log of 3. 8 is 2 cubed, so I'm going to make that 3 natural log 2 plus the natural log of 3, and then we could go back up here and figure out the numbers, okay? I think back in the days of slide rules, this was kind of a helpful little trick to do. It's just a nice little manipulative practice working our way through. Okay, so I'm going to leave those for you guys to try, give a shot at some of those, see if these make sense. And again, what you want to do is try to get it back into 2's and 3's and see where we are, see where we go from there, okay? All right, well, there's that, and there's that, and then back to here. So, I think that about wraps it up, I'm pretty sure. So this is going to turn out to be 1/3 the natural log of 12, just to get you started. This is going to be the natural log of 1 minus the natural log of 72. And I think that's all we've got to say. How do we do? 13 minutes, 38 seconds. Not bad. So, thanks for watching. See you tomorrow. If you have questions, feel free to ask, and enjoy the rest of your day. Bye-bye.